Kids, today I'm going to be talking about a couple things on the reference tables that we'll need to know to continue on with quantum modern physics. The first is the electromagnetic spectrum. We've seen this before on the reference table. Just take a look on the top. Wavelength, marked out in meters, 10 to the minus 7th meters, for example, is ultraviolet light. 10 to the minus 11th would put you in either X-rays or gamma rays, depending on whether the photon was ejected from a nucleus of an atom, in which case it would be a gamma ray, or if it was ejected in a more standard manner, that's an X-ray. Notice visible light is a very small part of the electromagnetic spectrum, just slightly in excess of 10 to the minus 6th meters. Microwaves can extend from nearly a meter long down to, a millimeter or a tenth of a millimeter. And you have even longer waves as radio waves here. If you look on the bottom part of this, and we're going to be spending more of our time looking on the bottom part, you'll see the frequency. The frequency is given as how many vibrations per second these things are doing, and you'll see the visible light spectra spread out here. So if we get an answer to a problem, and say we're calculating one of the calculations we're going to be doing in the energy level diagrams, and we were to get 5.10 times 10 to the 14th hertz, that would put it in yellow light. So that would be a chunk of yellow light. So we'll be talking about that. The frequency, notice these are high numbers, very large numbers. Notice the wavelengths are, in general, at least on the visible end of the spectrum, very small numbers. So the frequency is how many times a second the vibration occurs. What we want to look now at is the energy level diagrams. Okay, we have two energy level diagrams. This first is for a hydrogen atom. The next is for a mercury atom. They both work the same way. If we were to have an atom, okay, now imagine this is the nucleus of an atom, and these are the electron shells, and I'm only drawing a portion of the electron shells. And we could think of them as standing waves, because the electron is spread out. It is not a discrete particle. It is acting more like a standing wave. And this would be the lowest standing wave it can have. And like we were making standing waves in class, you have to wiggle it at just the right frequency to get it to go to the next level. And this would be higher energy, and progressively higher energies, till finally here it's infinite. You've liberated the electron completely. It's gone. On the side of your energy level diagram, you will see the energy. And the energy represents how much energy would be given off if it fell from infinitely far out, from where it was not attached to the nucleus at all, and how much energy it would fall. For example, if it only fell and stopped at the n equals 6, it would not give off so much energy, only 0.38 electron volts. The farther down it falls, the more energy it gives off. The maximum energy it could give off is 13.6 electron volts. Now, how would this energy be carried away? It would be carried away in the form of a photon of light. So we want to take a look at these, the difference in the energies from one level to another, and that'll give us a value in electron volts. We use multiplication by 1 and convert electron volts into joules, and then we use Planck's constant and convert that to a frequency. And we could see what frequency of light would be given off from each of these different falls. Conversely, if a photon came in and hit an electron down here, and the photon had 13.6 electron volts of energy, that electron could be kicked completely out of the atom. If it had less than that, it would not have any effect at all unless it had exactly the amount it took to kick an atom up to any of these particular levels. Then that amount of energy would be used to kick the electron up to that level. Okay, so let's try a problem first. We have 13.6 electron volts of energy released during the fall. Between this shell and this shell, how much energy is there? In other words, if an electron fell from here to here, how much energy would be given off? Let's take a look at the energy level diagrams. Well, we have 13.4 EVs here. I'm sorry, we have 3.4 EVs here, and we have 13.6 EVs here. So what's the difference between them? Simple subtraction. 13.6 minus 3.4 gives you 10.2 electron volts. Okay, so let's see what frequency of light that would be. So if we have 10.2 electron volts of energy, well, how do we turn that into joules? We just multiply by 1. So we know 1 EV is the same as 1.6 times 10 to the minus 19th joules. Well, what do we get there? All right, 10.2 times 1.6 EE 19 minus, that is 16, or 1.6 times 10 to the 1.6 times 10 to the minus 18th joules. Well, we use the formula E equals HF to convert to a frequency. We have the energy, we're looking for frequency, so E divided by H is going to be frequency, though. So the frequency is our 1.6 times 10 to the minus 18th joules divided by Planck's constant. That's 6.63 times 10 to the minus 34th joule times seconds. So we see the joules are going to cancel. We're going to be left in reciprocal seconds, which is good because that's hertz. And let's see what that's going to be. Divided by 6.63 EE 34 minus, and we get the frequency equals 2.5 times 10 to the 15th hertz. Now, when we take a look at what color light that is, we go here, and we see 10 to the 15th, be a little in here, we would get a burst of ultraviolet light. Well, that makes sense if you look at the energy level diagram here. That's a big jump to fall all the way here. That would be a sizable energy level jump to make that. How about if we had from the n equals 3 state to the n equals 2 state? Let's see what that would be. So n equals 3, and it drops to n equals 2. N equals 3 is 1.51. I know it's negative, but that's the energy that would be given off. We're just looking for the difference, 3.40. So just do some subtraction. 3.4 minus 1.51. That equals 1.89 electron volts. I got to make sure we're keeping our units. So 1.89 electron volts. What do we do with that? Well, we want to find the frequency. So first we have to change it into the energy in joules. So we multiply again by 1. So 1 electron volt is the same as 1.6 times 10 to the minus 19th joules. Let's do that. Times 1.6 EE 19 minus, that's 3.0. 3.0 times 10 to the minus 19th joules of energy. And we know that we're using E equals HF to find frequency. You're going to be dividing E by H. So let's just divide this by your 6.63 times 10 to the minus 34th joule seconds divided by 6.63 EE 34 negative. Well, that equals 4.6. 4.6 times 10 to the 14th hertz. Well, what do we get for that? All right, 10 to the 14th, 3.6, or I'm sorry, 4.6. 4.6 drops us into red light. So that would be a flash of red light if it was doing that. All right, how could we make the light a little bit higher? Well, if we look at the energy level diagram, we see that we need, If we go to this whole thing, it's going to be ultraviolet. So anything more than that is going to be either more ultraviolet or even higher energy. So let's just expand our range here. How about if we go from the n equals 6 level down to the n equals 2 level? All right, let's take a look what that would be. So n equals 6 down to n equals 2 level. So n equals 6 is 0.38. N equals 2 is, 3.40. So if we take the difference between that, that's 3.02 electron volts. We do the same thing again, right? Multiply by 1 eV is the same as 1.6 times 10 to the minus 19th joules. So 3.02 times 1.6 EE19 minus, that gives us 4.8 times 10 to the minus 19th joules. And if we divide that by Planck's constant, remembering E equals HF, and you're ending up just dividing by Planck's constant, 6.63 times 10 to the minus 34th joule seconds. So divided by 6.63 EE34 minus, we get 7.2 times 10 to the 14th. 7.2 times 10 to the 14th hertz. And what color is that going to be? 7.2 times 10 to the 14th, you can see that would be a burst of violet light. So this is how you work with these energy level diagrams. You can see there's really nothing hard about it. It is a weird place to be because it implies all sorts of oddness about the universe. And I hope you watched the videos before this because, yeah, that's what we're kind of talking about. But in its simplicity, in the mathematics, of course, is really very simple. And be aware, you can absorb a photon and jump, but it has to be exactly the right amount of energy. Exactly. Remember, these are standing waves we're making, and it's very much like pushing somebody on a swing. You could push them at exactly the right moment, or you're going to lose energy as you do it. Electrons aren't losing energy like that. So it has to be the exact amount of energy between these energy jumps, or it's not going to happen. So that's the whole big idea between energy level diagrams, Planck's constant, and our electromagnetic spectrum. Hope you enjoyed watching this, and stay tuned for more. Thanks, guys.